Welcome and hello. This is a video exercise in HEC RAS, and in this exercise, I'm going to be dealing with steady flow regimes and boundary conditions. So I'm going to be playing around with a few different steady flow regimes and boundary conditions in a simple steady state model here in HEC RAS. All right, what I have on the screen here is a brand new instance. I'm going to start by going File, New Project, navigate to the project folder. It's right here. Give the project a name. I'm going to give my title exercise 6.prj and then click OK. All right, already I have the geometric data window open. So go ahead and click on geometric data window or edit geometric data to bring that up. What I'm going to do here is just create a single geometric file and keep it constant and use that for the entire exercise. But what I'm going to do is change some of the flow data and then run some simulations and experiment with that. Right, so to start off, I'll click on the river reach button. I'm going to single left click at the upstream end of the reach and then double click at the end of the reach. You can add some intermediate clicks as well if you want to add some curvature to the reach, but I'm just going to go with this. I'm going to call this river A and reach 1. Okay, then I'm going to click on the cross section editor button and then add a new cross section at river station 0. And I'm going to type in my stationing data. So this is the station and elevation data for the points of the cross section now from left to right facing downstream. So 0, 90, the next one will be 100 feet over, and then the last point here will be at 1,000 feet over and to 90 feet elevation. Okay, the downstream length I'm going to say is 0 because this is the cross section at the bottom of the channel. Manning's end value, I'm just going to keep that at 0.03 for the main channel and 0.05 for the overbank area. Main channel will be from 300 to 700 in the cross section station values. All right, that looks good. I'm going to click Apply Button Data. Now I'm going to add one cross section at the top of the reach. Again, this is supposed to be fairly simple and straightforward. So I'm just going to make a copy of the current cross section. It's going to be at 100,000 River Station. So that's about 19 miles upstream if we're dealing with feet here. And then all I need to do here is type in a new downstream reach length values for the left overbank, main channel, right overbank, as well as increase these elevations. So I'm going to go options, adjust elevation, and then add 200 feet. So that would be 200 feet rise over 100,000 feet. Run would be 0.2%. Okay, so I'll click apply data, and then I can go plot, and then view the plot if I want. This is the profile. I'm going to add some intermediate cross sections as well. So let's do that. I'm going to close this data editor, go up to tools, cross section interpolation. Within a reach, I'm going to put a new cross section every 5,000 feet. See what that looks like. Okay, so that's good. Every almost mile, we'll say. Now I'm going to save this geometric file. So file, save geometry data. And then I'm just going to call this slope of 0.002 and then click OK. All right, now we need to go ahead and edit some of the hydraulic properties. Edit steady flow data. What we have here is I'm going to put in a flow rate of 100,000. So this is going to be a constant flow rate through the entire reach. Next, what we want to do is go with the boundary conditions. So for boundary conditions, this is something we're going to change up a few times in this exercise. I'm going to start with normal depth, and I'm going to start with a constant slope of 0.002. And then I'm going to click OK. I only have one profile, so it says profile all right here because this radio button is set to profile all. But then if I click on set boundary for one profile at a time, it's only for PF1, but that's pretty much the same thing because I only have one profile of 100,000 CFS. All right, so that looks fine there. I'm going to click OK. And now I'm going to save this steady flow data. And for the title, I'm going to call it normal depth, comma, slope 0.002. So that's the decimal of 0.2%. And then click OK. So I got that saved. I can close that now. Now I'm going to go ahead and actually run the simulation. So click on the steady state simulation, steady flow analysis. One thing I want to do is calculate the critical depth. So I'll check that checkbox on. And now with the geometry file and the steady flow file already selected, all I have to do is go File, Save Plan. I'm going to save this as the same name as the flow data, normal depth with the slope, and then click OK. And then same thing here, OK. All right, we're ready to compute. So it's running, and then I'll click Close. All right, let's go ahead and take a look at the results. I'm going to go View, Cross Section. And now we're at the very top cross section at the River Station 100,000. And then I could just toggle down. And as you see, it's the exact same profile. The only thing that's changing is the vertical axis is going down 10 feet because we have 20 cross sections with a change in 10 feet elevation each time. Okay, so I'm going to close that. I'm going to go back to my steady flow analysis. Now, as you notice, we use the subcritical flow regime, and that makes sense because when I open up the cross section, the water surface elevation here is subcritical. It's above the critical flow line, which is calculated here in red. And then the energy grade line is the green line up above. So if I went ahead and changed it to supercritical, so subcritical right here, it's basically going to constrain the flow to the critical water surface elevation or higher. Supercritical will constrain the water surface elevation to the critical water surface elevation or lower. And then mixed will allow the water surface elevation to fluctuate between anywhere, basically. It could be above or below the critical water surface elevation. The subcritical flow regime requires a downstream boundary condition. The supercritical flow regime requires an upstream boundary condition, and then the mixed flow regime requires both upstream and downstream boundary conditions. So to demonstrate that, I'm going to try to run supercritical flow regime. We should get an error message, and it's going to tell me that, boom, it's missing the upstream boundary condition for this particular reach. So what I'm going to do is I'm just going to go back to the flow data, steady flow data, click on boundary condition, and I'm just going to go ahead and select upstream, and then click on normal depth. I'm going to type in the same slope as the downstream boundary condition. In fact, I'm going to click on the downstream boundary condition, click delete, and then click OK, and then save that data. Right, so close that. Now I should be able to run supercritical. And as you'll see, we're going to have different results, meaning the water surface is going to be constrained at or below that critical water surface elevation. So this is what I mean. The water surface is definitely lower. I know I'm not looking at a table with actual values, but you can just see it's at the critical water surface elevation now. And that's true for all of the cross sections. Now, if I tried running the mixed flow regime, it's going to complain about not having a downstream boundary condition. See, so it's missing the downstream boundary condition. So let's go ahead and add that back in. I'm going to go to Edit, Steady Flow Data, Boundary Conditions, and then Normal Depth, 0.02, OK, and then Apply Data, which I believe is just the same thing as Save and Close. Save, OK. And now let's go ahead and run mix. Now this should result in the same results we had the first time for subcritical because this flow regime certainly is subcritical. I mean, unless you force it to be supercritical, which is not natural. All right, so let's take a look at those results. I'll go View, Cross Section, and here is the mixed flow regime results. You can see it's the same data we saw on our first simulation results for subcritical. We can also open up the table data. So go View, Profile Summary Table, and we see the Froude number is less than 1, so that's subcritical. Here is the channel invert. As you can see, it drops from 230 down to 30. Let me make this flow total column a little wider so we have a constant flow rate of 100,000 CFS. Here's the water surface elevation, and of course that's dropping 10 feet at each cross section, so it's just a constant change there as well. Next, I want to point out something on this table here. This is the standard table number 1, is we have a water surface elevation of 253.57 and 53.56. Another boundary condition is to actually fix the upstream or downstream water surface elevation based on that's just a different type of boundary condition. So that's what we're going to explore next. I'm going to close this, go back up to the steady flow data. Now I'm going to go File, New Flow Data. I'm going to name this new flow data Known Water Surface Elevation 255 to 55, which is going to be the upstream to the downstream. I'll click OK. I'm going to use the same flow rate. of 100,000 CFS. And then for boundary condition, I'll select downstream. Known WS is the water surface elevation. For downstream, I'm going to set it to 55. Okay. And then for upstream, known water surface elevation is going to be 255. So I believe using the normal depth boundary condition, mixed flow, and also subcritical flow regimes, the water surface elevation was like 253.7 down to 53.7 approximately. Let's go ahead and see if this new boundary condition changes that upstream and downstream cross section water surface elevation. So I'm going to go File, Save Flow Data. We can close that. I'm going to go and click on the Run Steady Flow Analysis. And what it's done is it's loaded in the same geometry file as before, but now it's loaded in the most recently created or most recently saved steady flow right here. So I don't need to make that selection. I just need to go ahead and save it. Save plan. I'm going to give it the same name as before, and it's giving me this pop-up here. So it's going to be called Known Water Surface Elevation 255 down to 55. Okay. And then same for the short name. I'm going to paste that in. Okay. This is mixed, which shouldn't be a problem because I have both upstream and downstream defined. And then I'll click compute. Okay, so that ran. I'll click close. Let's check out the cross-section data now. This is at 30,000, so let me go down to 0. And as we see, 0 looks pretty much the same or close to the same. I think it's a little bit above what it would be normally. And then if I go to the top, here's the top of the reach, and that looks exactly the same. So because this is subcritical flow, I believe only the downstream boundary condition was used, which was right here. Let's check out the actual numbers now. So I'm going to go View, Profile Summary Table. And sure enough, we have exactly 55 listed here as the water surface elevation in the 0 river station reach. And then at the top of the reach at 100,000 foot river station, we have 253.57. So this is the same thing as it was using normal flow. So it looks like the downstream subcritical flow regime governed, which makes sense because this is subcritical flow. Just out of curiosity, I'm going to go ahead and switch this to supercritical and then click compute. Now I think 255 will be the water surface elevation at the top. So I'm just going to go straight to the table this time, profile summary table. And it looks like it's actually lower than that because of the critical water surface elevation that it was constrained to be at or below. So let me just go ahead and peek at the numbers real quick, or the plot. Right, so 247 or whatever the critical water surface elevation is right here is below 255. We can also force this situation for every cross section. So that would just be the boundary condition called critical depth or critical flow, I believe. Let's go up to Edit, Steady Flow Data. I'm going to go File, New Flow Data. I'm going to name this one Critical Depth. Click OK. I'm going to use the same 100,000 CFS for the flow. And then for the reach boundary conditions, I'm going to use critical depth, both upstream and downstream. There's no need to specify any extra data or numbers like the slope or the water surface elevation, just critical depth. So I'll click OK and then File, Save Flow Data, and let's go ahead and run it. So I'll click on Steady Flow. I'm going to use critical depth as my flow file. That's correct. I need to save this plan first. So I'm going to call it, oops, I'm going to call this critical depth. Okay. And then for the short name, I'll call it critical depth as well. All right. We're ready to run critical depth compute. This is pretty uneventful. It's just going to be a water surface elevation held at the critical depth for every cross section in the reach. All right. The last boundary condition we haven't looked at yet is rating curve. So I'm going to go back to my steady flow data, file, new flow data. I'm going to call this rating curve now, and then click OK. I'm going to use the same flow rate of 100,000 CFS, and then click on boundary conditions. For downstream, I'm going to click on rating curve now. And in a separate Excel file I have right here, I'm going to just copy the stage and flow data that I have saved, Control C. And then if you come over here to the rating curve table and click Control V, it's only going to paste in the first cell. And that's a little frustrating because what's the point? But what I've noticed is if you just drag out the entire range that you're going to paste in or be more, then Control V will work. So right now at 100,000 CFS, I have it showing up at 55 as the downstream water surface elevation. So I expect it to be 55. Click OK, and then click OK right here. Okay, so that's saved as rating curve, file, save flow data, and then close. Now what I'm going to do here is use rating curve for this fourth plan and save the plan. I'm going to call it rating curve. Click OK. And then this is also going to be called rating curve. OK. Now, supercritical probably won't work. Let me just see. Yeah, I have a problem because, again, I need an upstream boundary condition if I'm using supercritical. Mixed will probably suffer from the same error. There it is. But that's all right because subcritical should work for me because I defined a downstream boundary condition for the rating curve at that river station 0 cross section. So I'll click compute, let it run. That ran just fine. I'll click close. Now let's go ahead and go view cross sections. Okay, it's at 30,000 again. Let me go down to 0. So here is the 0 cross section. Looks like it's right at 55, but we'll check the table. And then all the other cross sections look normal, just like the original normal depth simulation we ran. View profile summary table. All right, very cool. It looks like 55 is the water surface elevation at this cross section at River Station 0. And then all of the other cross section water surface elevations appear to be the same as the normal depth. All right, we have one final simulation to run. And in this situation, what I'm going to do is go to the flow data. I'm going to go File, New Flow Data, and I'm going to name this one Normal Depth Flow 100,000 CFS down to 50,000 CFS. So I'll show you what that means. I'm going to be using the same slope of 0.002, but I just didn't want to add any more to this title because it's already long enough. So I'll click OK. And then what I'm going to do here is at the top of the reach, River Station 100,000, is start with our familiar 100,000 CFS. Then what I'm going to do is change the flow rate. I'm going to come down 20,000 feet down to River Station cross section 80,000 and then click on this add a flow change location. Now I'm going to type in 50,000 CFS. And then for the boundary conditions, I'm going to use the same normal slope I did as in my original. Okay. And this is going to be subcritical flow, so there's no need to set an upstream boundary condition. So file, save the flow data. Now I can close this and then go back to run steady flow analysis. It has that most recently created and saved steady flow file. That looks good. I'm going to go file, save the plan. Okay, it keeps giving me this message. I know I need to save a new name. Here's the title, normal depth flow 100K to 50K. Okay. And then instead of rating curve, it'll be the same short ID here. This is subcritical flow. Everything looks good. Let's click compute and see what happens. Okay, so that appears successful. I'll click close. Now let's take a look at the cross sections first. I'm going to start up here at the top. This is 100,000 river station as well as 100,000 CFS in the flow. If I go down to 95,000, 90,000, 85,000, a big drop there, almost hitting critical flow, and then down to 80,000. So we see the water surface elevation really drop, and it appears to be constant downstream of 80,000. Again, 100,000, 95,000, no change. It goes up a little bit for 90, and then way down for 85, and then even lower for 80. This may be a particularly interesting plot to look at the profile. So if I go View, Water Surface Profiles, and then zoom in here on this upper part. So I'm just doing a mouse wheel to zoom and then Shift to get the pan hand. And also we could go Options, Landmarks, River Stationing. Yeah, so there's definitely the biggest drop in water surface elevation from 90 down to 85, even though it's at River Station 80,000, where we have half the flow rate we did just at the top of the reach. All right. So we can also look at the table that we've been looking at this whole time, View Profile Summary Table. And here we have the flow starts off at 100,000 and then it goes to 50,000. Here is the channel invert. Here's the water surface elevation. So it looks like the largest drop is right here of about 15 feet between these two river stations, because the invert only drops 10 feet. And another big drop right here in water surface elevation of about 13 feet, even though the channel invert only changes another 10 feet. We can also look at the water depth. So we have the critical water surface elevation, But if I want to add water depth to this table, maybe after water surface elevation, right here, I could go up to Options, Define Table, and then here I'm going to insert a column right here. So we'll say Insert Column, and then what it's called, I'm not sure. I'm going to search for depth. And of course, there's a bunch of different depth values. Okay, I think I found it. Max channel depth right here. I'm just going to double click and it popped into place here for my column 4, max channel depth, just to the right of water surface elevation. So I'll click OK, and now we have max channel depth. So it starts off at a channel depth of 23.5 feet. And then when the flow rate decreases from 100,000 down to 50,000, the depth in the same channel geometry, same Manning's end value, same slope and everything else is now down to 16 feet. And you can see the transition goes from 24, 19 to 16. So a lot of different random concepts involved with steady state flow covered in this lesson. We talked about the different boundary conditions, known water surface elevation, critical depth, normal depth, and rating curve, as well as the different flow regimes like subcritical, supercritical, and mixed flow.